Dakota here, starting a new channel called Mr. Sparks a Lot. It's going to be revolving around Tesla coils, high voltage, or technology, sciencey kind of stuff. Right now, Tesla coils. This video is my first video. Please bear with me. I'm not good at editing things or taking videos in the first place. So, if I tend to say a lot or something, just ignore that. I'm going to start off by just expressing a few points at the moment. The first major point I want to stress to you guys is safety. I'm going to be talking about Tesla coils in this video. I understand you guys think, oh yeah, they can't kill you. No, they can kill you, and they will kill you if you use them properly. We're talking about voltages that are enough to jump through the air. That's anything over 300 volts will arc without contact. We're talking about currents that could kill an elephant, and I'm not exaggerating that at all. It only takes around, I want to say 50 milliamps at the minimum to kill you. I'm not sure what the exact value is. I have looked it up multiple times and found multiple different answers, so I'm going to go with 50. You do not want to get shocked with anything over maybe 20 milliamps because that really hurts and it'll knock you on your ass. Now, the next point I'm going to get across is I'm going to show you in this video my Tesla coil. I'm going to explain the Tesla coil and kind of explain some theories with it, with breaking the laws of physics, and that would be the law of conservation of energy. I'm going to kind of break that myth about Tesla coils with a little bit of simple math. It's not all going to be there because I don't want to blow your guys' minds away too much. And I am going to be using a computer program that is free online, and I'll discuss that later with you guys. So, hope you guys enjoy. Okay guys, so now we're going to draw you a schematic here. I'm going to make it really sweet and simple and quick and easy and whatever you want to call it. I've been having problems with my camera, so it keeps cutting out for no apparent reason. Alright, sweet and simple. There we go. So, I'm going to make this easy for you. I'm going to first start by explaining how this all works. And I'm going to do it in two separate parts because my camera's being a little annoying. This is my neon sign transformer. This takes 120 volts in, puts out 7,500 volts at 240 milliamps. So, 0.24 amps. This charges the tank capacitor through, I'm going to go ahead and ignore that, charges my tank capacitor through my primary coil. Then, once it's charged, we ignore the transformer. It essentially does nothing at this point. The capacitor discharges through the spark gap, creates a spark in the spark gap, and through my primary coil. Now this induces a current at, according to some calculations, 1,600 amps. Now that's approximation, but that is the maximum instantaneous current. That 1,600 amps, now you're thinking, where did I get 1,600 amps? And I'm going to explain that in just a little bit. Transfers my now 10,000 volts, again, I'm going to explain this a little later, through an inductive field or electromagnetic field to my secondary coil here, just like a transformer. Now that is then stored in the top load until it can't hold back the energy anymore. So then it discharges as a spark. So now I'm going to tell you kind of about this math and how all that works. So, let's think of this as a water slide. Water slides are fun. I like water slides. I remember a water slide when I was young. I'd go to a water park and they had at the top of the water slide a nice big water tank. And if you were the lucky fellow who got to go down the slide with the water tank, it was the most fun you've ever had. Now that water tank is being filled with a little hose here, a little tiny hose, real slow. Maybe, let's say it takes 5 minutes to fill that water tank all the way up. So the little hose is our power supply, and the water tank is our capacitor. And the slide, our primary circuit, primary capacitor, or sorry, primary coil. Now, the little hose, as our power supply, is charging the tank. Takes a while. Once that tank is charged, or the water is all the way full, it releases all at once. All that energy in that capacitor, or all that water in that tank, is being released down the slide, or through my coil, all at once. So, some of the math behind that is our charge takes 0.016 seconds. Approximately. I think it's actually a little bit less than that. Or, no, a little more than that. Anyways, our discharge, or the time it takes for the water to empty the tank and go down the slide, is 0.0000021 seconds. And that was calculated way before here. It's actually saved up in my brain right now. We're going to go ahead and divide that with my trusty calculator over here. We get, let me do it real quick, 0.016 divided by 0.0000021 equals 7619. Approximately. I took off the decimal, don't need it. That number has nothing to do with my coil at all, other than it's kind of like a time coefficient. Basically, my input current gets multiplied by this, and my input voltage. So input voltage times current times this number. So my input voltage and current gives me 1,800 watts, or VA for AC. That multiplied by this gets me, so 1,800 times the above number gives me 13,714,285 watts on my output. That is how much is in this circuit. And that will transfer to this equally, because there's no more capacitor steps or anything like that to charge up like the water slide. So, I'm going to go ahead and calculate this wattage value, which is pretty simple. It's going to be the 16 million watts is my approximation according to this. So, as you can see, they're definitely, 3 million off. But when you're talking about these numbers that have to be absolutely perfect, and you're talking about 100% efficiency in both this transformer, the spark gap, the capacitor, everything, those numbers are going not add up, because the efficiencies are all different. But they're close enough. If I go on in Java, the program Java TC, Java Tesla Coil, Java TC, it gives me a lot of values. That's where I got these values from. This is, again, a rounding. My actual voltage here is something like 8,900, something like crazy like that. So it actually ends up being about 14 million watts. That is my average there. That is my actual output. That equates to about 800,000 volts at 18 amps on my output. That is a lot of power. Here we are. This is the Java TC program. It is actually online for free, whatever. Classic Tesla. You can search Java TC, it'll come up. There are lots of different resources here. Different calculators. Even has the creator of the website's coils here. shows all of their coils. Start off with select units, inches, ambient temperature. It starts you off at 68 degrees Fahrenheit. That's pretty accurate for where I am. Copper as my main uses here. Primary wire type is round, not ribbon on mine. I'm going to go ahead and enter my 0.15 microfarad capacitor as my primary capacitor. I'm going to enter my ground radius as 100. That's a good radius for indoor use because there's a lot of ambient, or I shouldn't say ambient, miscellaneous metal objects that are grounded around the Tesla coil. That's for indoor use. Now my secondary coil, I'm going to start with a 3.125 lower radius and a 3.125 upper radius because I'm using 6-inch PVC. My height for low voltage is going to be 20. This is just for the image later. You could say 0, but it kind of messes up the image. Doesn't really matter. It actually is, I want to say like 15 inches above the ground in reality. That does actually do something when you're talking about the ground plane. 20 is probably a good number here though. And then my top is going to be 50 because it's 30 inches of windings. There are 1,100 windings. 22 gauge wire is what I used. My low voltage radius for my primary coil, that's the inner radius, is going to be 5 inches. The outer radius is going to be 7 inches. My height is at 20. It's at the base of my my secondary coil. It is 3.5 turns of 1/4 inch copper tubing, so 0.25 for wire diameter. Toroid, that is my top load. My top load is a toroid. It is a donut shape. I'm going to put 4 inches as my minor diameter, 21 inches as my major diameter, and I'll go over that kind of later, what those mean if you don't understand. It is at 54 inches above the base. I'm going to add that. Now I actually have 2, so I'm going to add my second one. Is 12 inch my major diameter, and it's 52 inches above my base. Go down here, click run. There's all my nice values. It did all the math for me. It's pretty accurate. First 2 things here are the most important. For anyone who doesn't want to get too into the Tesla coils, those are your most important numbers right there. 164 kilohertz, 164 kilohertz. Notice how they match. Mine's pretty spot on. Yours doesn't have to be that spot on. That would be the best efficiency. You could have it a couple percentage off. It tells you my percentage off right here. I'm 0.48% high. No big deal. You could be a couple off. I would say try to keep it within 5% if you can. If not, who knows, you might get better sparks. It really depends. The other important thing is the aspect ratio. Height to diameter. Mine is 4.8 to 1. You want to keep it within 3 to 1 or 5 to 1. Anywhere in between is perfect. Anywhere above or below, you're kind of pushing it. You have to do a lot of tweaking to get them to run good. This is the image I was showing you about. If you put 0, it starts you off like way down here. If you put 15, it's like right at the base. So I just put 20, I put it right there. I probably should go with 15, but in this case it's such a minor change, it's not going to do too much to my output. I'm going to scroll down here, my rated voltage in for my power supply. Now, I have to stress that you have to enter this in before you can do anything below it. This takes everything else into account. My input is 120 volts. My output of my power supply is 7500 volts. Milliamp 240, hertz 60 because I'm in the United States of America and that's what it is. If you are in the United States of America, it is 60 hertz, most likely. Most likely in any other country it's going to also be that, or 50, but 60 is a good value. Put 120 as my applied voltage in, because that is exactly what I'm doing. Calculate this. Now, rated transformer VA, or watts, essentially. 1800, as we saw earlier. Transformer impedance, effective output voltage, effective input current 15 amps, all this fun stuff. So, here, hold on a minute, where's it at? There it is. Voltage across the capacitor, 10,607 amps, or sorry, peak volts, not amps. I read that wrong. That is the maximum voltage that the capacitor will see. Even though it says 7,500, it will see 10,600 volts. I need to discharge it before it gets to that value, otherwise I'm going to be breaking my capacitors, and I don't want that. So that's going to be later for the spark gap. Recommended capacitor rating, 26,000 volts. Mine is only 12,000 volts because I'm using a MMC, which is multiple capacitors in series parallel. I'm using 36 capacitors. They're each 2 kilovolts at 0.15 microfarads. 36 of them, 6 by 6, will make 0.15 microfarads at 12,000 volts. My joules, primary capacitor energy, 8.44 joules is the maximum energy that it builds up. Primary instantaneous current, 1,641 peak amps. That's where I got that value from earlier. The cool thing is it tells you what your average spark length should be. You can actually click all these and it'll give you a detailed explanation what it all is. It should be about 61.3 inches. I'm shooting for about 60 inches. It's probably, good value, 5 feet. Secondary base current, 21.8 amps. That is the most current that your secondary will ever put out. Even if you only have, the same amount of turns as your primary, that is the most it will let you put out. We're going to kind of go down. This is a rotary gap design. I actually have a static gap. I'm going to go ahead and put this in. Now again, you cannot enter this unless you enter everything above except for rotary gap. You don't have to have that. Mine's a static. I'm basing it off of 6 electrodes, each with a diameter of 0.5 inches because it's half-inch copper tubing. My total spacing, I'm going to put 0.125, so 1/8 of an inch. Pretty good spacing. It'll tell you down here. See, if I put, let's just say, let me just put in 1 inch. It's going to tell me gap distance is too wide. So you got to bring it down. 0.125, that's my value. It's going to tell me spacing between each electrode, 0.025 inches. Charge voltage for the capacitor is 10,600. That gap arc voltage is going to be 10,300. So I'm 300 volts below my maximum voltage. This is the maximum spark gap that I should have. I really should go a little smaller with it. My original one was actually going to be 0.1. We'll see what happens there. Yeah, 877. That's what my 8,900 was from my 8,900. I'm going to go back to my maximum just to kind of show you maximum. It shows you field strength, shows you volts per unit, shows you percentage of the cap that is charged. It'll show you the time to arc. So, 15 milliseconds. Time to arc. Let's read that. Time required to fully charge the capacitor to charge voltage calculated. Now my calculated value was a little off. So, again, some off values. I was basing it off of my previous numbers and I changed them since. Breaks per second, 67. That's my 60. That's where I got my 60 hertz from. Effective cap energy tells you that again. Terminal voltage. This is the voltage off the top of my secondary. 798,223 peak volts. Now again, this is based off of everything above. Could change, could slightly change. Different atmospheric conditions. Everything is accounted for. Power delivered to the gap is 530 joules per beat per second. Static gap spark length, 61.8 inches. Again, 60 inches is a good value to shoot for. You can go down here, you can put format as text, it'll give you all this. You can copy and paste it to a thing, save it, whatever you want to do. You can make a load file, you can select the text, whatever. If you don't know how to copy and paste, you probably shouldn't be on your computer. Can't really see the bottom of this. I'm going to kind of move the camera a little bit. Run voltage and current distribution.
Gives me this nice lovely graph. Sorry you guys can't really see the bottom of it, can't scroll down any farther, and I don't really want to move the camera. Shows you, at the bottom it says, right about here is 5 inches, 10 inches, 15, 20, 25, and 30. This is my length of my secondary coil, and these are my output values. Very bottom value for current in amps is going to be about 18 amps. The very top value is 22.5 amps. Very top value for voltage, 800,000 volts. Very low value is basically 0. Or, yeah, 0. At my output, my current, can't really see it, it's all the way at the bottom, is about 18.1 amps. Very high voltage is, again, the 790 whatever thousand volts, so about 800,000 volts there. If I were to tap it off at any of these points, it tells me the voltage and the current per that specific point. Again, the maximum of 22.3 amps on the primary. Alright guys, back again. Here's the Tesla coil base. As you can see, I don't have the top on it. I'm actually going to have a piece of plexiglass bolted onto these things so I can pull it all apart when I need to. So I'm just going to start off by saying this is my power supply right here. These three. There is actually supposed to be a fourth one right here. That's why there's a space. I haven't gotten it yet, so it's not complete. Yeah, I know. I'll post some videos later when it's done. So on this side here, kind of move it over, maybe you can see the side a little better. I have, power comes in right here. It's a nice audio jack, got 15 amp connectors on there. That comes in, goes through a 15 amp breaker into a power switch. So my main power switch turns on the whole system. That sends power to my step-down transformer. This supplies my 12 volts to my low voltage controls. It's a pretty simple setup, basically just a relay to turn it on and off. I don't have a variac, they're like $250 unfortunately. This is my cat Tiger. He gets locked out when I turn it on because I don't want him dying. Go over there, go over there. Okay, so anyway, basically just a rectifier, capacitor over here, 12 volts. That comes in right here. This is my plug, goes to my control box. I'll show that to you right here. It's kind of spooled up. I don't feel like I'm spooling it right now. I have my safety key. It is a key. I can pull out the key. When that turns on, this yellow light turns on, and when I'm finished, it'll have lights on here that will also turn on when the safety is live. Then I have a main power on-off switch, and about 25 feet of wire. That triggers my relay. My relay is a 30 amp 250 volt relay. That powers into all my NSTs phased parallel. These will all be connected. I don't have my high voltage wire yet either. I did have this operating at one point. I wasn't using near the type of wire I needed to be using, so I'm not even going to bring that up right now. I want you guys to be safe. The other thing I'm going to stress a lot in this video is these can kill you, and they will kill you if used improperly. Please be safe. Don't try to touch it. Don't sit on top of it. Chainmail suits are fun. Make sure you're completely covered. I haven't done it. I've seen it done. Just be safe. Okay, anyway, back to the test coil. There will be 4 of these. Each one of these is 7,500 volts at 60 milliamps each. So altogether, be 240 milliamps. Rotate this around. When I turn on my system, 12 volts comes through this wire here. It's going to be kind of shoved in between. It'll be fine. And goes over to my spark gap. You can't really see inside it right now, unfortunately. I have it closed up. It is actually 8 different electrodes. I can tap off on any one of these contacts here. kind of see them there. It has a fan on top, sucks air in through the top. There's also a fan in the bottom. The fan helps blow the air out sideways instead of straight through. That way I could mount it this way. All of my 12 volt connections are up here, away from any electrodes, very far away. Only have it duct taped for now for testing. It will be finished. Get out of here, kitty. And the whole thing's on wheels, so it's easy to move. These are bolted down. They actually can come out. I'm not going to take them out, but they can. And now we're going to move over to the actual Tesla coil. I'm going to start off with the base of the Tesla coil, as you can see here. I'm just going to pull this off. It's not all together yet. This is my primary coil. You can see that it's about 5 or 6 turns. I think it's 6 turns. It's actually going to be tapped off. This is going to be the start, and this is going to be my finish. That is 1, 2, 3.5 turns on the primary coil. It's 1/4 inch copper tubing. This is my strike ring. You always need a strike ring. You don't want the electricity going back into your primary circuit. It will fry your electronics and could potentially come back and bite you. It probably won't, but you just want to make sure you're safe. This will be grounded to earth ground and the bottom of my Tesla coil secondary. On top of that goes my secondary. As you can see, it will be mounted right there. This is 1,100 turns of 22 gauge wire. Bottom of this, I have a little crimp-on connection. That's actually just going to be clipped on with the wire that I use, so that I can easily take it apart. Now I'm going to kind of move the camera here, and then we'll be right back. Okay, I moved the coil. So now you can see the whole thing. Again, the coil itself is 30 inches. You can add like a 1/2 inch on the bottom there, and then maybe 1 inch on the top there between that and the top load. I did kind of lie. It should have been an extra inch up on the Java TC program. That extra inch actually doesn't make too big of a difference. I did the calculation, so you don't really need to worry about that. You can see it is aluminum dryer ducting, cardboard in the center, and then metal tape for the top load. And that is connected with a bolt in the center, and there's a wire connected to that that is connected to the top of my secondary.
Alright guys, hope you guys enjoyed my video. If you got any questions or comments, you can go ahead and post them below. I will be accepting video requests if there's any kind of science experiment with the Tesla coil, high voltage, or anything related to my future videos. I'll be kind of posting more of what I can do, what I can't do later. I will be accepting video requests for putting things on the Tesla coil, having them struck by the Tesla coil. Now, be reasonable. Don't say, oh, go buy a brand new television and get it struck by the Tesla coil, because I'm not going to do that. Simple things, a couple little tricks I'll be showing you, different light bulbs, things like that, in future videos. Again, I hope you guys are safe. Don't walk up to them and touch them unless you know that it's safe to do so. I do have some of mine that are safe. I have done calculations and I have done tests to make sure that they are safe. But still, if used improperly, I could get hurt, and I don't want to see that happen to anybody, resulting in watching my video.